absolutely delighted to be part of this international collaborative network. So in this presentation, I will give you a brief background of my PhD project, what are my general objectives, study area, and key findings from 3 different chapters, and what are the implications of my PhD project. Arable land and water are the 2 principal natural resources in Pakistan. Arable land is 22 million hectares, that is about 1/4 of the total area of the country, irrigated by an extensive contiguous gravity flow irrigation network called as Indus Basin Irrigation Network. About 75% of this arable land is irrigated mainly through this irrigation network. Main cash crops in Pakistan are cotton, wheat, rice and maize. So agriculture is the mainstay of Pakistan's economy, contributing about 21% to its GDP and applying about 45% of the total work labor force. Rice is a highly valued cash crop of Pakistan, grown on an area of 2.7 million hectares with a total production of about 6 million tons. In recent years, there has been an increase in rice production mainly because of an increase in rice area. Rice is grown in 4 different zones under diverse climatic conditions. Zone 1 is located in the northern mountainous areas with subhumid, subtropical type climate. Zone 2 is the broad strip of land between 2 rivers, Ravi and Chenab in Punjab province. And in this area, more than 50% of rice area is cultivated and produced. Zone 3 is the west bank of the river Indus with a tropical type climate. And Zone 4 is the Indus Delta with a tropical marine type climate. If you look at the rice graph, around 2000 there was a decline in rice production due to the El Nino and drought stress, what we mentioned already in project. And also in 2010 we had a severe flood. 2 extremes of water affecting the rice production. And also in the future, the declining water availability would be the main concern to sustain the increase in rice area and production, because irrigated agriculture is currently facing a water deficit of about 20 billion cubic meter, which is projected to be about 27 billion cubic meter in the near future. In order to supplement the insufficient canal water, farmers have to supply the groundwater, and the costs of groundwater are increasing day by day due to increase in diesel prices and electric tariff. Besides water shortage, another major constraint to rice production is the low land population, because the contractual labor paid on area basis tends to leave patches in the field during transplanting, and that ultimately results in lower panicle number and reduced yields. So in order to improve the resource use efficiency of scarce resources of labor, water and energy, I am investigating aerobic rice system as an option for improving resource use efficiency in rice-based systems of Pakistan. The general objectives of my PhD study are to quantify the crop performance of selected genotypes in aerobic rice system under water and nitrogen limitations, to improve our ability to predict phenology of modern aerobic rice genotypes under different environmental conditions, to calibrate the Epsom riser model, and to propose locally adapted systems, and to understand farmer perceptions about aerobic rice in regards to future adoption. I did field experiments in the district Faisalabad, and I did farmer surveys in 3 different cropping systems. The green one is the typical rice field system. The blue color represents the central Punjab with a more mixed cropping system, and below you see the lower Punjab predominantly the cotton wheat system. So in addition to the field experiments and farmer surveys, I did a growth chamber experiment to probe into the pre-flowering photothermal responses of aerobic rice genotypes. Photoperiod sensitivity complicates the estimation of a large number of required parameters that characterize phenological development and hence impairs predictions. Phenology calibration based on field experiments is especially difficult because of the two main problems: finding the start and end of the photoperiod responsive period and disentangling photoperiod and temperature effects. So in this study, we followed a two-step approach. In the first step, we determined the photoperiod response by conducting an experiment with different day lengths at a fixed temperature of 26 degrees Celsius. And in the second step, we combined the obtained photoperiod parameters with phenology observations from field experiments to determine the temperature response. The specific objectives of this study were to present a two-step approach for estimating the photothermal phenology of 4 selected rice genotypes and study how well phenology can be simulated when using standard cardinal temperatures of 8, 30 and 42 degrees Celsius. That with an increase in day length, the number of days to flowering increased in all 4 tested genotypes because rice is a short day plant, and this indicated that all 4 tested genotypes were photoperiod sensitive. We also did the reciprocal transfer of plants between a short day chamber of 10 hours day length and a long day chamber of 15 hour day length and found these patterns. Statistical analysis of these patterns resulted in the estimation of the photoperiod response parameters, and we determined the length of 3 successive pre-flowering phases. Basic vegetative period, that is when plants are still insensitive to photoperiod sensitive phase under short day and long day conditions, and post photoperiod sensitive phase. So from the length of these 3 successive phases, we calculated the FOP, that is the minimum number of days to flowering at optimum photoperiod of 10 hours, theta 1 and theta 2, that are the start and end of the photoperiod responsive period. So in the next step, before calibrating temperature, we checked if the standard cardinal temperatures 8, 30 and 42 degrees Celsius, how well they represent our data. And we found that the number of days to flowering was severely overestimated. This was in the order of 20 to 35 days with 0 hour twilight, and more when we added 0.9 hours of twilight. And this corresponds also to the 2 recent studies by Zhang et al. And Fanut et al. That question the validity of these 3 cardinal temperatures that are commonly used in rice model and also series rice model. Subsequent optimization of cardinal temperatures through an improved calibration program, we found a range of parameters value for base temperature, optimum temperature and maximum temperature. But we could not converge to a unique set of optimal parameter converges. Despite this lack of apparent convergence to a unique set of optimal parameter sets, all near optimal parameter sets had one thing in common. They all simulated slower development below around 31 degrees Celsius and a faster development above 31 degrees Celsius for both a bilinear and a beta model. So our conclusion from this study is that we have got a robust set of photoperiod parameter sets for 4 important genotypes that could be used in the future studies, but the temperature response was, the estimation of temperature response was hindered by a too narrow range of temperature conditions because we had only one temperature in growth chamber, and the temperature also didn't vary during the growing seasons in 2009 and 10. But these robust set of photoperiod parameter sets could be used in future experiments like with different planting dates or quantifying photoperiod by temperature effects. Now I would like to move to the field experiments. These are the results based on analysis of variance. So we found an interaction between irrigation and genotype for days to flowering. In 2009, days to flowering increased as we increased the water stress, and even at the highest water stress, the number of days to flowering were more than what we found under what we normally find under the flooded conditions. So this had great implications for resource use. So if we are going to adapt aerobic rice system, then we have to develop the shorter duration varieties. And we also found an interaction for grain yield and water productivity based on grain yield. The lower is for represents the results of same experiments with 3 local genotypes in 2010. But the main difference between these 2 years is that in 2009 we had only little rainfall during growing season of about 200 millimeter, and in 2010 we had 3 times higher rainfall. And for this we found the main effects of irrigation for shoot biomass, panicle number, harvest index, spikelet fertility, 1000 grain weight, total nitrogen uptake, and water productivities, but we didn't find an interaction between irrigation and genotype. Grain yield was highest in the high irrigation treatment, that was about re-irrigation at about 80% of field capacity. These are the 3 local genotypes. KSK 133 is relatively drought tolerant post-grain genotypes. RSP1 is a new line being developed with the aim of drought tolerance, and IR6 was an old introduction from IRI in 1970. So the grain yields of KSK and RSP were within the target grain yields of for aerobic rice system set by IRI of about 4 to 6 tons per hectare. But as we increase the water stress level, the grain yields decline. And also these grain yields are less than the yield potential of these varieties of about 8 to 10 tons per hectare. The differences in grain yield and water productivity were strongly associated with the panicle number and harvest index. In 2010, we also did an additional experiments in which we tested 2 improved genotypes that are APO is normally used as a control in aerobic rice system, and it is a suitable variety for tropical conditions, and IR7371 is also an important drought tolerant line commonly used in breeding programs. But we found that compared to local genotypes, the grain yields of these 2 exotic genotypes were similar at the high irrigation treatment, but under water stress conditions, the grain yields of these 2 relatively drought tolerant genotypes were better than the 3 local genotypes. This is the graph for water productivity. Above is the graph for water productivity based on total above ground shoot biomass, and below is the graph for water productivity based on grain yield. So based on total above ground biomass, the water productivity was comparable among 3 irrigation treatments in 2009 and increased as we reduced the water input in moderate and low water treatments. But on the basis of grain yield, the water productivity was highest at the high irrigation treatment. Still, there is a scope for increase in yield if we increase the water level. That's what we expected. But the water productivity, we found values up to 0.38, that is significantly higher than a national average value of 0.16. Now I would like to share some of the results of the farmer surveys. I will show all the numbers. The specific objectives are to understand and analyze farmer perceptions. So we did interviews with 3 different groups of farmers who tried aerobic rice already, who did not try aerobic rice, and those who are not growing rice at the moment. And we found that the current awareness of about aerobic rice system is very low. More than 50% farmers are still unaware of this aerobic rice technology. Regarding positive attributes, farmer perceived aerobic rice as a means of increasing resource use efficiency, particularly for labor requirement and water saving, net profitability, and an option for crop diversification in the mixed cropping zone. The main perceived threats were weeds, diseases, poor germination, spike elasticity, and low yields, and the need for frequent irrigation requirements, because some farmers think that it needs more frequent irrigation requirement that is difficult to maintain compared to current conditions. Those who tried aerobic rice were very positive about planting it again, but the response differed between the two districts. In district Hafizabad, more farmers were willing to try it, and this was basically related to the size of their land holding and the soil type. In district Hafizabad, we had more number of large farmers that are land size more than 10 hectares and clay soil. The deciding factors for planting again were ease of operation due to direct seeding, better income, low input requirement, especially for labor. And deciding factors against planting again were unavailability of suitable basmati type varieties, falling water table, and weeds. Among farmer groups, farmers who are already growing rice are more likely to adopt than the non-rice farmers. So the implications of this project are that aerobic rice is potentially an interesting alternate evident from high values of the water productivity and the farmers' positive response to experiment with it. Grain yields are within the target yield. Producing more rice with less water was not possible in this case, but the saved water can be used to irrigate the previously unirrigated area, or there is another option that farmers might sell the saved water to neighboring farmers and raise their income. Unavailability of suitable basmati type varieties is a major constraint, and we need well adapted varieties for this. So this project has implications, so I will skip this part and I will focus only on crop modeling, because these questions I would like to address through this APM project. So based on the findings of this study, I would like to capture the effects of water dynamics in relation to management issues such as irrigation and fertilization, accurate simulation of phenology and genotype specific delay in flowering as a function of drought stress, that is probably possible through riser model. This has great implications for overall resource use, accurate modeling of how yield components are affected by drought, and to study the trade-offs between yield and resource use efficiency. Thank you very much for your attention.
Questions?
Production increased because of increase in area of cultivation. But your slide shows that it is not area is not increasing. Production only increasing.
In the non-traditional rice belt, about nearly 1 million hectare more area was brought under cultivation, because we have problems with other crops like cotton and sugarcane due to the long duration of sugarcane and due to more pest attack on cotton crop and the rising cost of production.
It may not be statistically viable. Statistically, it may not be.
Not modeling data, 2 years of field
Validation. Yeah, we are further with crop modeling. We are
that is just to see.
but only
develop some scenarios.
He cannot do more than 12 years.
PhD.
You said 2009, how much? What was the rainfall?
About 200 millimeter
What about
during
2010?
600
What
millimeter.
is the yield level in 2009 and 10?
The highest yield level in 2009 was about 4.5
10?
tons per hectare,
10? 2010?
and in 2010 it was like 5 tons per
But
hectare.
did you find any drastic difference between 2009 and 10?
Yeah, in 2009 we had an interaction between irrigation and
Not irrigation, it's a total yield.
The yield and productivity, what
we can't say the drastic differences, but still there were some minor differences. because we were applying the irrigation based on
No,
on
even
the
if you
soil
put
moisture.
irrigation also,
Yeah.
did you find any difference? Even
The fully irrigated.
Yes, even fully irrigated also. Did you find any appearance and the yield level? I think that it should be less.
In 2010,
Dry year.
yeah, the yield levels overall they were
It was
less,
less.
especially over the moderate and low water treatments.
Another important factor, you are doing a very good job here, but only thing, what physiological aspects which we are studying to advise the breeders to choose a trait?
Yeah.
Any maybe
Yeah.
transpiration studies and all?
We did measure the physiological parameters, but obviously the short duration,
Well, you had the yield components.
the gene components, the short duration and harvest index, and panicle number. These are some of the things that we advise.
How you are establishing your aerobic system, like your direct sowing,
Yeah, it's direct seeding and
puddling.
no.
So similarly, what we did in like similar.
Immediately irrigated or you just sown the crop on rainfall and then you have gone for irrigation? How you do?
No, we did prepare the land in proper weather condition, proper moisture condition. We sow the crop, and after about 1 week we applied the first irrigation. And we have applied the first two irrigations uniformly to all the treatments to help crop establishment.
Okay, and then I think we better move on.
Well, one of the important aspects of Awan's study is that he wants to use that experiment for modeling, for the long-term modeling, in order to put the 2 years in perspective. And one of the issues there was that none of the existing models could really handle the phenology, which is why he did the detailed cross-chamber analysis for phenology, which can now be used to put up price models. Because the biggest bottleneck that we have at the moment is that we have predicted phenology with models that are notoriously bad at handling phenology, whilst phenology is one of the crucial components when it comes to predicting yields. And to some extent, it puts in question a lot of the modeling studies if we don't have the phenology right. And it's an ongoing problem with modeling that we just need to be aware of whenever we embark on a modeling exercise. Because if the phenology is predicted incorrectly, it invalidates a lot of results.
The phenology prediction is a big problem with all the models. Certain models are predicting early plantings better, certain models are predicting late plantings better.
Thanks very much, Howard.